So, so this is a slide that I generally like to show you why we actually need programming. Okay, so I actually got this from XKCD, or I can't remember where I got it, but basically, if you think about how you actually do a certain computing task, okay, so there's always the manual way, right? You can manually change the parameters and then run the calculations again, and then change the parameter again and run it again. And the thing about this kind of approach is that you can make actually fairly good progress in the beginning, right? Because you don't spend time writing any script or programming software, right? Now, unfortunately, there is always a crossover point, right? So whenever you actually have a lot of calculations to do, all right, there is some point where if you actually spend the time to actually write a good script, you subsequently the time spent on actually running the calculations becomes negligible, and you actually get a much greater output compared to doing it manually. Okay. I would say that the calculations you have done in lab number 2 is sort of at the somewhat at this threshold already. You actually did quite a good number of calculations because you actually have to keep doing calculations with different energy cutoffs, different K points. So that is actually a good number of calculations to actually show you the power of programming. Okay. So there are four, as in all kinds of knowledge, there are definitely a lot of different levels of attainment. Okay, so so this is of course adapted from Star Wars. So as you all well know, May the 4th was just a few days ago, so this is actually quite timely. So where most people start off at the lowest level, which is the youngling level. Okay, so you actually do a lot of things manually. Maybe some things that can be automated, you don't actually do. You don't actually automate them. Uh, you tend you tend to make lots of mistakes. For example, you sometimes type you have a misspelling in some of your variables or in one of your input files, and then you have to redo your calculations, and then that actually takes a long time, right? Now, with lab number 2, you guys should be actually at about this level. You now know your way around the command line. Maybe you know some basic shell scripting. You'll even know a little bit of programming to make some tasks easier, right? Now, once you actually have to do a whole PhD in QM modeling, all right? So if you actually have to spend day in, day out time to actually do calculations and analyze the calculations, you can actually get to this level, right? So you actually spend you spend a lot of time mastering programming to a good level, right? So you can write fairly sophisticated shell on programming scripts. You can plot results, and by the end of your PhD, you can even try to find a job in a software company, right? Now, the final level is something that actually very few people get to, right? So this is really the level where you don't just write scripts or program for yourself, right? You actually are able to write proper software frameworks that are reusable and extendable by other users. Okay, so my rule of thumb is if you have not written a software that say another 100 other people have used, you basically have not gotten to this level. Okay, so if it is just a script that you and maybe a few collaborators use, that's really not a proper software framework. Okay. Now, let me start with the most basic type of scripting that you guys have encountered. And that is basically the Unix command line, right? The most important command in the Unix command line is man. Okay, so man just stands for manual. Okay, so at any point in time, if you want to know how to use any of these commands, you just type man, that command name, and then what you get is a documentation on what that command does and how do you go about using it. And usually that that manual page also has a lot of examples for you to just copy and paste, and then you can get around to doing stuff. Okay. Now, other than man, there are a few other Unix commands that you should be familiar with, especially once you get as you go along. You probably have already used some of this during your lab number 1 and 2. Okay, so these are just the basics. Okay, there are literally hundreds of Unix command lines, command line tools. Okay, these are just some of the ones that is more useful to you. Okay, so for example, grep is a command that searches any given input files, and you can actually search them for lines that match one or more patterns. So you have used this in your lab number 1. Okay, that's basically what this command does. Another command is called cat. Cat basically just reads the files sequentially and then writing them to the standard output, or you can actually dump it to a file as well. So you can actually combine files using the cat command. Okay. SED is actually a command that allows you to substitute strings in files, right? You can actually read in a file or a string, and then you can substitute, say, I want to change the basis set from 6-31G to 6-311G, okay? Now, so SED is actually quite a powerful command. In fact, with SED, potentially you can actually avoid having to do any programming altogether, because quite a lot of the changes you want to make to input files, you can actually accomplish them using SED, right? So a long time ago when I first started out as a grad student, I actually used SED a lot, okay? Head and tail just basically displays the start and ending part of the file. This is useful because a lot of times the initial input variables that you are using for your calculations are at the front part of your file, and the results that you really care about are in the bottom part of the file. Okay, so if you remember during your lab 1, you look at the log of the Gaussian of the NWChem calculations, you notice that the files are actually fairly large, right? So you actually have some initial part of the file, and then there's lots and lots of logging occurring while the calculations are being performed. So there's they actually output the energies at each ionic or electronic step. So a lot of times you don't actually care about the intermediate steps. You only care about what the final energy is or what the final geometry is. And these two commands can be quite useful. Okay. Find is basically a command that allows you to recursively descend into a directory, and then you evaluate an expression for each file. So this is actually a very powerful command. Be very careful when you use it, because if you use the wrong command, you can actually delete all your files. Okay, so but if you want to go through, say, if you have organized your calculations in terms of like multiple subdirectories, and you have subdirectories of the underneath the subdirectories, and you just want to get, for example, the last part of every single calculation that you have done, using find would actually be quite a useful way to do it. Okay. Less is basically just for you to view the file in the terminal. All right. Now, regardless of the commands, there are also different types of Unix shells. Okay, they broadly fall into two main types. Okay, so one is called the Bourne shell, is the de facto standard. So nowadays, when you log into most of the Unix or Linux systems, you are confronted with a Bourne shell. Okay, there's another Unix shell called C shell that uses C language-like syntax. Some people prefer that because they are very good C programmers, and that syntax is a lot more familiar with them. There's really not much of a capability difference between the two. I would just say you just choose whatever you're most comfortable with, and you just learn to work with that particular shell format. Okay. All right. Now, beyond just typing commands into the terminal, the next level is what are called shell scripts. Okay, shell scripts are essentially short scripts that you write using a sequence of shell commands. Okay, and with shell scripts, you also have some level of flow control, right? So, for example, this is an example of a very simple shell script, which basically says that, well, I'm going to set the current working directory to the, this pwd command is basically the current path. I'm going to set the cwd variable to the current directory, and then I'm going to find everything, all the subdirectories within this current directory, and then for each of the directory, I'm going to go into them, and I'm going to execute some commands, and then I'm going to come back out to the main directory, and I'm going to loop it through all the subfolders. Okay, and this is basically this is actually a very useful, I would say, template for you to work with different to execute commands on all your subdirectories. For example, let's say you want to you want to actually grab the data from every single a particular file in every single directory. This is basically something that you can adapt to use it. Okay. Now, the main thing about programming is always about flow control. Okay. Flow control just simply means that it is a mechanism in which you can modify the sequence in which a set of statements or instructions are basically being executed or evaluated, right? There are two broad types of, of flow control. One is called conditional. In other words, this is your typical if-else statement or case switch statements. You only execute certain commands if a certain condition is met or some other condition is met. Okay. Now, there's then the other type of flow control is basically loops. This is what you have seen in your lab number 2. For example, your for loops, your while loops. They are quite similar. The syntax is a bit different. The use cases that you might actually apply them to is a bit different. By and large, I would say most of the time you're using for loops, and this was what you use in your lab number 2. All right, so you may ask, why can't I just do everything with shell scripts, right? You can, right? So in fact, in your lab number 2, if you wanted to do the whole lab number 2 in shell scripts, you can actually do it, and it wouldn't actually be all that much different from that Python, the short Python script that I've just written for you. Okay. Now the good thing about shell scripts is, first of all, they are ubiquitous, right? Once you log on into your Unix shell, you basically have access to shell scripts, right? You can get started very quickly. You just fire up your editor, and then you can just write something. And they are very useful for short programs or scripts with just a tiny little bit of flow control. Okay, and however, they do come with some very significant cons. Okay, so the first very big con is that they are very error prone, right? Especially if, let's say, you have written a shell script which is more than 100 lines, and if you make an error in, say, line number 2, by default the shell script is going to just keep going. Okay, so if you have made any small bit of error, and that error actually can cascade down into very serious consequences down the road. Okay, so this is why in general I don't recommend you use shell scripts when you are dealing with anything more complex than, say, 30 or 40 lines. Okay. The second con is even doing some simple math is ugly, right? So you see these examples here, right? So let's say I just want to add 1 to 5, right? I basically have to call this function called expr, and then I actually have to use this $sign, and then if I don't actually put a space around that plus, I basically just get 5 plus 1. but if I put a plus, space around the plus, I actually get the proper correct answer, which is 6. Okay, so doing math is just extremely difficult with shell scripts. Okay, and if you want to do any matrix math or anything more complex than that, then you can forget about it, right? So, and for a lot of us, when we are dealing with analysis of quantum mechanical calculations, we want to do fairly complex math with them, right? So we want to do things like change of units. We will need to do second derivatives, which is what you want to do, which is what you did in your second lab, and all those things is going to be extremely difficult to do in the shell script. Okay, it's also difficult to extend and build on, right? So it's rare that you see, like, for example, class inheritance or one shell script depending on another shell script, right? Just simply because it's not meant for that purpose. Okay. So now, once you go beyond shell scripts, then you enter the world into the world of proper programming languages, right? And here you basically have lots and lots of options, right? So what I show you here is basically a alphabet soup of all the programming languages out there. This is a bit outdated already. The larger the size of the letters, the more popular in general the programming language is. And of course, you can see things like Java or Python. They are among the most popular languages around here. Okay. All right. What are some pros and cons on programming languages, right? So the pros is, of course, number one pro is that they are far more powerful than just your simple shells. Okay. The next one is also that many of them, they do come with extensive libraries. In other words, what either is built into the programming language itself or things that other people have written that makes a lot of the stuff that you want to do a lot easier. So in other words, for example, if you want to do a second derivative, you are not going to write the program to calculate the second derivative yourself, because someone else has already written it for you. Okay, so there are extensive libraries that makes things like math and plotting a lot easier. A lot of the programming languages, especially the more popular ones, do come with support tools. So for example, you can use IDEs that help reduce bugs when you are actually writing your programs. Okay, and if you actually use them properly, you can actually write very useful packages that a lot of other people are using, that a lot of other people would use. Okay. Now, the cons are, of course, that if you are using a compiled language like C, you require an additional compilation step. So in other words, you would need to compile your program before you can actually run it. There's an additional learning curve. Okay, so the power comes with the expense that you actually have to learn the syntax. You actually have to learn what's the proper way of writing the program, how do you organize your files, and so on and so forth. And finally, not all programming languages are supported on all systems. Okay, so this is usually not an issue with the popular programming languages, but of course, if you are determined to use some new programming language or some esoteric programming language, this can potentially be an issue. Okay. All right. So the question then is, which programming language should you choose, right? The short answer is, of course, well, you can use whatever you're most comfortable with, right? Say you are an expert C programmer or you are an expert Java programmer. You can by all means use those languages for whatever task you are that you want to do. Okay. But the longer answer is really it depends on what you need it for, right? So if your performance requirements is critical, right? So in other words, you are writing a code that is doing something extremely expensive to do, okay? And you want to squeeze every single bit of performance out of that, out of your program, you then would usually have to go with compiled languages like C or Fortran, right? So this is the reason why codes like NWCam or PWSCF, they are not written in any of the interpreted languages, okay? You actually go with compiled languages like C and Fortran, and you optimize the hell out of it, okay? Now, but at a higher level, if you are not the person developing the DFT code, you are the person who is using the DFT code, and then you are trying to do analysis, and you are changing the code all the time, and you're trying to basically modify the code to do different things, then speed of development and prototyping is much more important than raw performance, right? You don't care if that grabbing that one piece of information from that file takes a few milliseconds longer. You care if having to take that data out of the file requires you 10 times the time to code or less, right? Now, if this speed of development is more important to you, then scripting languages like Python and Perl are generally easier to get into, okay? So for the purposes of this class, we will exclusively use Python. So I'm not giving you guys a choice. So you're not going to use C or anything else. You are going to use Python, and most of the scripts I provide you are in Python, okay? So this is an XKCD cartoon on Python. So basically this is about this guy who just learned Python, and then because he basically just he's so happy that he had learned Python that he's basically flying, okay? So now what is Python, right? Python is a general purpose high level programming language, okay? General purpose means that you can do most things with it. High level means that you don't usually get down to the nitty-gritty parts of what machine you are using to run your Python program on, that sort of thing, okay? Most of those details are taken care for you, right? Python, the design of Python also emphasizes code readability, right? So later, as you will see, the way that Python programs are written is that they use indentation to basically separate out blocks of code. And because of that, when you read a Python code, it's usually a lot easier to understand what it is trying to do, right? Unlike, say, for example, C or Java code where it can be really hard to read, right? It supports multiple programming paradigms, okay? So if you are into object-oriented programming, or if you want to do imperative, functional, or procedural programming, all those paradigms are supported within Python. It is dynamically typed with automatic memory management and a large standard library. What this simply means is that out of the box, you can already do a lot of things with it, and you don't actually have to worry about memory management, all right? So this is unlike, for example, C, where you actually have to say, well, I'm going to create this variable, I want to assign how much memory to this variable, okay? In Python, for the most part, you don't worry about those things. Basically, the interpreter is going to take care of all of those things for you, right? And that makes it a lot easier for, say, a beginner programmer to get into, right? It is also available on almost all platforms, okay? So at least some version of it, right? So this just shows you the a comparison of the three programming languages. Let's say you want to print hello world in Java, C++, or Python. In Java, you basically have all this templating stuff. Okay, so all this craft, you basically have to call a public class called hello. You have to specify a main method, and then you call system.out.println hello world, right? C++, there's all this syntax which can look confusing. You basically have to take the string and you dump it into the standard out, and this is basically how you do hello world in C++. And in Python, it's basically just print hello world, all right, full stop. So you can see why Python has become such a popular language, right? So unless you need the performance of, say, C or C++, it's a lot easier to just type hello world, right? All right. Now, The other nice thing about Python is that because so many people uses it, an entire set of scientific computing libraries have been built with Python, right? So in other words, nowadays when you want to do most stuff, you can basically, you don't even have to write a lot of code, right? So there are already libraries that are written for you to do most of the stuff, or at least help you do most of the stuff that you want to do, okay? So the key ones are what I have given here, right? So the first one, the fundamental one, is called NumPy. NumPy just stands for numerical Python. It defines things like the array, the matrices, and how do you do, say, a matrix operation such as a dot product, matrix multiplication, calculating eigenvalues and eigenfunctions, and eigenvectors, and so on and so forth. All these things are implemented within NumPy. And NumPy at the base level is implemented in C. It only exposes a Python interface, but the underlying code is actually in C. The underlying implementations for most of it is actually in C, and NumPy is extremely fast, right? So when people say Python is slow, actually, I would say it's usually a misconception. You can actually, because a lot of the underlying stuff is written in underlying C code, in compiled code, the performance is usually quite comparable to what you get with compiled languages, okay? The next one is called SciPy. This adds on to NumPy things like some numerical routines for integration and optimization, and a lot of other capabilities such as statistics and that sort of thing. So this is the second package that most of you would actually work with in terms of Python libraries, okay? Pandas is actually a very interesting library. It basically just defines a data structure that is sort of like, think of it like an Excel spreadsheet, but is dumped into a Python object. And it is actually extremely powerful if you are doing any form of things like programming, machine learning, or AI on your data. Then Pandas is one of the packages that you will most likely be using to manipulate your data structures, okay? And finally, matplotlib is something that you use to do plotting of your data. So you can do some, the 2D plots are really good. The 3D plots nowadays is getting better, but they are still not as good as, say, the 2D plotting capabilities, okay? And finally, you have your IPython or Jupyter notebook, which allows you to actually do the coding within within a browser, and it is actually a very useful way for you to quickly process data and test programming ideas, okay? So here are some resources that you might want to read. So for example, the Python documentation is at python.org/doc. There's also the NumPy docs that would be very useful for you if you are going to do some manipulation of going to work with some matrix multiplications and that sort of thing, okay? Now, beyond all this scientific programming packages, there are also a lot of packages that have been written specifically for material science applications, okay? So for example, there is Pymatgen, which is the code that I created. This stands for Python Materials Genomics. I'm going to talk a little bit more about this. There's something also called the Atomic Simulation Environment. This is a code that is actually even earlier than Pymatgen. There's a little bit overlap in functionality, but the key focus of ASE is a bit different. ASE is meant more as a way for you to quickly generate simulations, okay, to help you run simulations, while Pymatgen is really more for the analysis of your calculations, okay? And there's also other packages like aflowlib and so on and so forth, okay? Now, so what is Python Materials Genomics, or Pymatgen, right? it is the core materials analysis library that powers the materials project today. Okay, it defines things like Python objects for representing materials data. So for example, you want to represent, say, a molecule or a crystal structure. Pymatgen defines objects to represent those kind of things. Okay. It also defines a robust set of structure and thermodynamic analysis tools. Okay, so for example, let's say you want to create a new crystal structure by substituting one of the atoms with another type of atom. This kind of structure manipulation, all those can be done within Pymatgen. Okay. Or if you want to do thermodynamic analysis, like calculating the equation of state, which is what you did in lab number 2, or calculating a phase diagram, or that sort of thing, all these things are also implemented within Pymatgen. Okay. Now, Pymatgen is also open source. In other words, anyone can download it. They can look at the source code. If they find errors, they can tell us about the errors. If they want to add on new tools to Pymatgen, they can also do so. Okay, so in fact, there have been a lot of contributions from the community in terms of different types of analysis you can do with Pymatgen. Okay, so this is just a quick overview of what Pymatgen does. Okay, so typically you start with some structure or data input. So for example, your calculation input or output files. VAS is the type of code that we use in the materials project, but you can also use something like, say, there's also something that supports NWCAM. There's also something that supports PWSCF. You can read all those results into, say, Python objects. Things like a computer entry basically stores the results of a calculation. There are also objects representing, say, the density of states or the band structure of a crystal structure. And then you can do all your analysis, right? So you can plot your electronic structure. You can calculate things like the effective mass. You can also, there are also some application specific properties. Like, for example, you want to calculate the voltage of a battery. There are tools within Pymatgen to do that. Okay. All right. So this is just an example of how you use Pymatgen. So for example, there are objects representing the elements. Okay, and this objects actually contains a lot of useful information about the elements, right? So for example, you want to know the atomic mass of silicon. You want to know its melting point. There are also objects that represent the composition. So for example, let's say I want to create a composition called Fe2O3, and I want to know what the atomic weight of Fe2O3 is. I just do comp.weight and it gives me the weight. Okay, and of course there's ways to construct crystal structures. This actually shows you how to construct a cesium chloride, cubic cesium chloride structure, and you can calculate things like the volume, you can also construct them from space groups. You can analyze what symmetry space group that structure is in. Okay. All right. So with that, I just want to give you a final word on programming. Okay. What I have done is just to give you a very broad overview, starting from why do you want to learn programming to some of the libraries that you might potentially be interested in learning to use if you want to become a proper modeler of materials. Okay. My word is this, right? That we go back to the first 2 slides where I showed you basically that if you spend the time to write a program, you can actually increase the efficiency of what you do subsequently, right? And this goes to learning programming languages as well. So that you will have to spend time learning all the commands, the syntax, and how to most efficiently write a program, right? But that investment in that learning actually can yield a lot of dividends in your efficiency as a materials modeler, right? So I can give you one example, right? When I first started out in my PhD, there was no software framework for writing, for generating a large number of calculations, right? So my efficiency was very low, right? To do say 10 different structures, I will spend one whole week doing it, right? Just to change my input files, I made a lot of mistakes. Sometimes I type a 1 when I meant to type a 0, and then I have to redo my calculations, right? Nowadays, with a lot of the software frameworks that have been written, most of my students can actually start running 10 calculations is nothing, right? Most of my students can do 10 calculations in less than an hour, right? And this is something that is the result of writing proper software frameworks for doing large-scale calculations, right? And there's this very famous quote from Abraham Lincoln, which says that, well, give me 6 hours to chop down a tree, I'll spend the first 4 sharpening the axe, right? So this just simply means that it is more important to make sure that your tool, you work on the tool set that you are going to use to perform a task. And so in your case, sharpen your axe, right? Learn programming well, and that will always help you down the road, okay?